First, of course, I would thank everyone for coming and listening to this webinar. I hope the information will be useful for you, and you will use the AIMNet potential with IMS. It's really cool that IMS implemented AIMNet to make it accessible for many people, many of your customers. I am not anyhow affiliated with IMS. As a disclosure, so I will present my own work and what we're doing and what IMS people implementing in their software. So what we actually do in developing ML potentials is taking the molecules, taking some quantum chemical method, calculating properties, and doing this for many systems. And out of this huge database that we collected, we train a model that reproduces QM properties. Well, since we are working on potentials, first and foremost, it's energy. And you can imagine this being what we actually do is we're making a lot of quantum chemical calculations in advance. And after this, you can use the model in a much lower cost because we took all the cost, all the computational cost some time ago in the big computers. And how this actually works, it's everything in our group. And well, way before it was a little bit different group. But everything started with ANI potentials, and it was a good breakthrough in the field to make the potential that's generally applicable to organic molecules, not system-specific, not something, but well, it was neutral organic molecules. There were, of course, limitations, but it was, it was, and it is now. It's still usable, and it's implemented ANI 1, ANI 1X, ANI 2X, 81CCX models implemented in IMS. So the idea is it was blazing fast and reasonably accurate. And since I'm here, just a quick note for everyone to see what the difference between at least ANI models. I will talk about AIMNet a little bit. ANI 1, ANI 1X that's implemented in IMS, suitable for neutral CHNO organic molecules. ANI 2X extends elements to CHNO, sulfur, fluorine, and chlorine, 7 elements. There is internal architecture difficulties implementing many elements. AIMNet doesn't have it, but this is for ANI 2X, 7 elements, neutral, and ANI 1CCX. And those two were trained on the hybrid DFT double zeta basis set. And ANI 1CCX is trained to couple cluster data for based on ANI 1X model. So it's CHNO and couple cluster like accuracy. And I said what we're doing, and first why. Then I will say why we're doing this. This can imagine like standard trade-off between the cost and accuracy of computational methods that probably every one of you know and familiar. And there are also some limitations, like force fields are blazing fast. They might be accurate, they might be not. It depends. It's really difficult to make force fields universally transferable to different kinds of molecules. And as we go to sophisticated methods, DFT and high-level correlated methods, they're universally applicable, but they're and have high accuracy, but their cost is prohibitively high. Well, we're moving there to the heaven. And our idea with development of null potentials is yet somewhere in this green dot. So have DFT-like accuracy, but the cost, well, practically it's somewhere between semi-empirical methods and force fields. And well, it's a little bit different. Scale of these methods are still linear or quasi-linear, but the cost is of course higher than standard force field. And before we go into the details of the results and high-level overview, what we can do, just a few words, maybe a little bit complicated. I don't want to scare you too much with this, but basic idea how AIMNet model works. It's like any computational method in AMS, in Gaussian, whatever you know. The input for the model is our atomic coordinates, Z atomic numbers, and Q total charge. We need total charge, and it's important. And then some magic here occurs. We compute features of the local environment of each atom. We're doing message passes, and we're doing charge equilibration, very rudimentary, but very computationally efficient. But we get at the end local atomic energy, and we have approximation that total energy is sum of atomic local energies. Plus, we're also doing explicit long-range terms, dispersion term, which we use Grimm's D3 correction, and Coulomb electrostatics. And just I will talk a little bit more about this. There's one number missing from, at least from Gaussian, but I don't know AMS well. It's spin multiplicity, which is simple. Could be implemented in this architecture, and we implemented this. It's just not a single charge, but two charges, alpha and beta total charges, and it can do spin polarized systems. There is no fundamental difficulties with this. And even before I go to the results, just to show that it's useful and it's fast, there are two plots showing computational scalability of the model. Probably I'll start the one on the right. This is on the best GPU that we can find, H100. We can fit 1,000 in the single GPU. We can do 1,000 hundred thousands, maybe somewhere close to 200,000 atoms. And scaling is linear, and we need half a second for 100,000 atoms for energy and for force evaluation. And graph on the left is a little bit tricky to interpret, but we compare with two of our major competitors, force field and semi-empirical methods, and the one that implemented NextDB, beautiful software by Grimmie. And basically, what this is end-to-end computational efficiency comparison. We compare the total time which is needed to optimize medium-sized organic molecules. Whatever optimizer we use, XTB uses better optimizer. But if everything implemented right, you will not get these numbers in IMS. I will explain why. Because we use batching to saturate GPU at full, and we have batched optimizer. But in a nutshell, on the CPU, the performance AIMNet model on the single core is about the same as semi-empirical, and on GPU, it's about the same order as force field. Force field on CPU. It's not fair, but that we got. So you have the idea. And if everything implemented super efficiently, we can use like 0.1 seconds to optimize a molecule on the GPU. Make dozens and dozens of geometry optimization steps. Okay, and first outline what I'll be talking about today. The AIMNet2 models. This is foundational. This is the most established, well-working model that is actually implemented and attached to AMS. I will talk about spin-unrestricted case. It's not went public yet, but in principle, it could be used with AMS. There's the same model. If you're interested, you might contact Alexander Isaev, see if you want to test try this models or something. I will talk about another developments. It's a reactive model, so highly accurate description of transition states for CHNO organics. The model for palladium-catalyzed reaction, and a little bit about our model for protein crystal structure refinement, which is really cool development. Okay, so first and foremost, I've talked about the architecture. If I'm talking about the what AIMNet2 can do, we're looking at the data set it was trained on, and you might have an idea what it can do. It cannot do things that were not in data set. And the data set, we basically use so-called data distillation process. We took low fidelity DFT, really cheap DFT, B97-3C, and compute maybe total more than 100,000 molecular conformations, non-equilibrium different molecules. And then we selected, iteratively selected the data needed. Well, we selected 20 million, which if trained to, it's good enough to describe all 100,000, 100 million molecules. And those molecules have 14 chemical elements. It's non-equilibrium conformations, and we did not target just organics. A lot of structures were from PubChem, so it's a lot of element organic molecules. Those weird things that you see in the slide, and AIMNet can work with those things. Of course, it can do normal organic molecules in different charge states, but with the same accuracy, it can handle non-standard bonding situations. Few benchmarks. One is very important. People use it a lot. Torsion scans. It's by the way, I forgot to mention. We for AIMNet, we use two methods. One is cheap B97-3C, which you can see as the model in AMS. Another one is omega B97M with triple zeta basis set. So it's a range separated hybrid. It's one of the best DFT functionals available in the market, though it's pretty expensive to calculate, even these small molecules. Okay, moving on to results. Decent torsion scans, and generally way better than GFN2-XTB. And we're comparing with another model, Orbnet-Delany. It's a so-called transferability model. So it needs it's a model built on top of XTB output. So it's not cheaper than XTB. But though it's a pretty good one. But anyway, for standard torsion scans, it's already better than GFN2-XTB. AIMNet is one of really few models on the market that is general enough to be applicable to the most of GMNTK55 dataset. It's gold standard, one of the gold standard dataset for benchmarking quantum chemical methods across different tasks, different elements, charge states, intermolecular barrier heights, a lot of subsets. So, in general conclusions here that AIMNet2, well, it's generally pretty much outperforms GFN2-XTB, and in many cases getting closer. So AIMNet train on omega B97M. In many cases, it's pretty close to inexpensive DFT B97-3C. So of course we cannot. We only can be as good as our underlying method is, but with a good underlying method, we can, with some accuracy loss, we can reach the accuracy of B97-3C. Another benchmark here is NCI Atlas. It's intermolecular interactions for small molecules, dissociation curves, intermolecular for small molecules. And what is in here, it clearly shows XTB fails for ionic hydrogen bonds, which is well, for ions, for charged systems, XTB doesn't work well. Where AIMNet shines, it doesn't basically produce the same accuracy for charge and neutral. Though for we would like, and we're working on this to have much better accuracy for intermolecular interactions. Application for unusual bonding. I don't know if it's, yeah. We made a procedure to look into CSD Cambridge Crystal database and extract molecules with the most unusual chemical bonding. So those chemical situations, chemical bonding that has least number of representatives in the CSD. And there's some examples from that list. It's very, I would say, interesting molecules like this one, 6-coordinated chlorine minus ion. It's a true story. It's there. It's crystal structure. It's experimental. And our idea was, can AIMNet at least not explode with the structures? It works. At least we can do geometry optimizations and have decent quality of optimized structures. And well, overall, RMSD 0.4 angstrom from crystal structure geometry, which is, again, I would say decent. And based on this thing, we developed a benchmark. It's a little bit difficult to explain, so I get in detail. So we had not that crazy molecules, it's only molecules that work with OpenEye Omega. We love this software for conformer generation. So we took molecular graphs for those weird molecules, and only those that have MMFF 94 force field parameters within OpenEye Omega. So OpenEye Omega can do conformations for those molecules. And for each molecule, we're making a conformational ensemble. We optimize all those conformers and see, look at the conformation which is the closest to the experimentally observed, and look on its energy. It should have either it's mimicking standard conformational work, conformation search workflow. So in this case, we're trying to find something that's if we match an experimental structure, and the match structure should have low energy. And those are the results. So things within red rectangles represents the structure. Each point is conformation ensemble, and it shows if it has close to experimental and low energy, then it's we have the match, and it's within this red rectangle. And overall, AIMNet for these benchmarks, mindless confirmation benchmark, I would say. It greatly outperforms GFNFF and GFN2 XTB, and AIMNet trained on Omega B97M. Again, it's pretty close to B97-3C, the DFT method. So it's very good result. Next chapter, very briefly, AIMNet2 NEC, that's in development. We're performing a few tests and benchmarks before we can publish this model. So the basic idea is to extend AIMNet2 first data set and then the model towards spin-unrestricted case. And this is the procedure how we, again, mindlessly generated a good number of training data points with unpaired electrons. We took the molecule to closed shell and added electron, removed electron, delete hydrogen atoms, unpaired electron, making triplet, and just add these two data sets together, train. Well, first good thing, I'm showing this briefly, performance on our base benchmark GMTK 55 and NCI Atlas is not much worse. And so the model keeps and can accommodate both well, this more complicated data, I would say. One of the reasons why we use this model sorry, is to study radical reactions. And those are some profiles with radical reactions, and see the model performs, I would say, very well, both for reaction energy and activation energy. And if you look closely on those, we have a huge database of these radical reactions. And if you look DFT versus AIMNet, well, DFT is hybrid DFT. The AIMNet was trained to hybrid DFT. In this case, we didn't bother to train GGA for open shells, of course, but because there are a lot of might be a lot of problems with this. But the AIMNet trained on hybrid DFT versus DFT is much better than GGA DFT versus hybrid DFT. So, and again, it's a very cool result showing the accuracy of this model. And what it can do with this, it study reactions. One is interest reaction. It's one of the core reactions for polymer chemistry. This dissociation of the molecule bond breaking and dissociation on the two radicals, and this is how AIMNet describes this versus the ground truth. Shaded area is prediction uncertainty. Well, first it shows pretty well singlet triplet. It shows the area when it should be crossed, when it goes from singlet to triplet. But the good thing that the areas where you see huge uncertainties, and basically it's this is AIMNet doesn't get this answer right. But again, it's okay just because it's high energy states. It's singlet when the bond is broken. It's not the state you're usually interested in. You're interested in the lowest energy state, which is triplet in this case. So having errors in this area and this area is okay. For the most energetically favorable, right, the uncertainties are decent, good, everything's accurate. More examples of radical reactions. It generally works on the it's not never perfect when you, well, not supposed to be always perfect, and there are some errors for the barrier height, but in general it can describe this reaction. And at very, very least, I will talk about this more. You have decent transition state geometries which you can refine with accurate quantum chemical methods. If you don't trust AIMNet, we need to make sure that accuracy is good. Another chapter, again, very quickly development in our lab, the model for reactive CHNO chemistry, very accurate. So this plot basically shows the atomic embeddings. It's a 2D projection of some atomic embedding, the properties of the atoms within the 3D molecules, this specifically carbon atoms. And green, red areas represent the atoms in equilibrium conformation, and green are transition states. So basically, when you go into transition states, you have much broader chemistry. The properties of the atoms are much broader. So you need to and if you only train on red, you probably could not describe all the greens. So that's why we need a lot of sampling to get the transition states right. So this is work that have been done in our lab, and Dylan Anstein is doing this. Again, the publication is about to be ready. Develop special data sets for CHNO chemistry, and he was targeting all sorts of the reactions, and the model is, well, extremely accurate for transition states and wide range of reactions. And well, what we're doing, been doing for months is probably just collecting feedback and trying to find the cases where it fails. And pretty sure its model is stable and well, very broadly applicable. And what's cool about this model for reactions and the main purpose? It's exploring so-called reaction network, the degradation networks or other things. When you the molecule has so many possibilities to react and do this some sequence or network graph of reactions, and that might be even for a simple molecule, it might be hundreds of possible chemical reactions, and it takes a lot of computational time to explore this reaction network with traditional computational methods. What we're actually doing, it's the beauty of GPU implementation of our models, well, whatever, any ML interatomic potentials, that we can do batch calculations, and GPUs have a lot of processing units, so it can handle a lot of molecules. And we have an algorithm to stack different NABs for different molecules, not just elastic band calculations, and do many reaction passes at once. And we can study, well, million reactions in 3 days on a GPU. So it's really cool application for high performance exploration of reaction networks. Another model, another chapter here, it's a model for palladium-catalyzed reactions. So everything that you heard before this point was organic or element organic. Here comes the metal, probably one of the simplest metal to model because it doesn't have tricky, weird spin states. It's just palladium. And the palladium catalyzed reactions are cornerstone of synthetic organic chemistry. It's one of the mostly used reactions, CC cross-coupling reactions. Though the catalytic cycle in of this Suzuki reaction is a little bit complicated. It has few options, few options how things could develop, and it has 3 major stages. So it's a little bit also challenging to model. So for this reaction, we developed a data set. We again mindlessly sampled the different stages of this reaction with different ligands, different organic molecules, and collected good data set that we believe is good, and try to apply this trained AIMNet model to this, try to apply and see would it be useful for modeling palladium catalyzed reactions. So we first it's a benchmark of energies of intermediate complexes. Well, here you see DFT overlap of DFT optimized and AIMNet optimized complexes of different stages of the reaction, and they're very, very close. So for geometry optimizations, AIMNet performs here very well. For the energies, it's also the accuracy is, well, probably decent and good, and the method could be used to model the energies of different complexes. And here we try to reproduce, well, with a simple set of ligands, simple reaction, but reproduce all the stages of the reaction. And here is, well, reference DFT. That was it's one of the foundational works for the mechanistic studies of palladium catalyzed reactions, published 2010. Very simple system, but we with AIMNet we reproduced all the stages, all the transition states, and get, well, RMSE with respect to reference DFT about 2 kcal/mol, both for intermediates and transition states. And here are the overlaps between DFT and AIMNet optimized structures for transition states and intermediates. So, and here I would say, well, we again we are finalizing the publication of this model. It will become public. And what's good about this model, even though it's might not give the energy as accurately as you want. Some people say, hey, 2 kcal/mol is too much for a transition state, and maybe they're right. But at least AIMNet can do decent transition states and can save a lot of CPU time when preparing this transition state search. And of course, this model is a little bit more than just Suzuki reaction. It can also can do decent, good geometries for palladium complexes in different oxidation states, including bimetallic complexes. And another, sorry, and probably the last chapter here, it's model for crystal structure refinement for protein structures. Well, what you can see on this slide on the right is what actually observed experimentally, and on the left. And what you can see on the right is the model that scientists built to describe this observed electron density. And this is process called refinement. Getting from left to right is called refinement of crystal structure, protein structure, in this case. And the final model have to be not just reproduce the density, the observed density. It should be correct from the structural viewpoint. So the bonds should be there, the topology, the amino acids as we know them should be in place. Bond lengths, bond angles, torsion angles should be reasonable. Secondary structure should be reasonable. To achieve this, what's usually used is some compromise, weighted compromise between the observed density and some restraints that forces model to have correct structure and chemistry. And here we have, on this picture, you can see two cases, the same fragment refined with and without restraints. And without restraints, of course, they even phenyl ring, benzene ring would not be flat or even connected, just because not enough information here to conclude this just phenyl ring. But we know it's there, so we put this in the model. So the idea is called QR, quantum-based refinement. The publication is under review right now. This QR project was going many years. There are a few publications on this, and the team who was developing this project targeted well, using quantum chemistry to compute those restraints, because usually it's force field or something even simpler than a force field, standard force field. But they try to use quantum chemistry and see if they can improve the models. It was very promising. The models were improved, but the computational cost, as you can imagine, was tremendous. And we try to plug AIMNet model specially trained here. So we collected the data set from the small, computed the interactions and conformation of small peptides, build a model, and here are the results. So if you try to do geometry with this model, we try to do geometry optimization of the high quality protein structures. And well, with different, try different methods to see which one, the AFT methods, which one will work the best. And we selected B97M 𝗗𝗃𝗋𝗃. Well, we have to go up to 𝗗𝗃𝗃 level with careful consideration of everything, so everything works properly up to that level of theory. But it well worth it, and the model overall is good. So one of the problems that we get with this model was as little as confirmation of arginine. So the pyramidality of amino groups in arginine, and many different computational methods give very different pyramidality. This is the distribution of the set of those good quality proteins, and this is the reason why we choose BD7M-D4, because it gives the answer that we know is correct. It should be almost planar, or at least not hugely pyramidal. And those are results is the AIMNet refinement. It's implemented in Phoenix refinement software of the crystal structures. Shows the models indeed are very much improved compared to the standard restraints that I used, that did not that are not even a force field, simpler than a force field, doesn't give better hydrogen bond secondary structure overall information. And probably with this, I will conclude my talk, just saying overall that we are working on making these models flexible, being able to accommodate very diverse chemistry and different bonding situations, and can be used as a replacement of standard high quality or semi-empirical methods. And also it's not enabled in AMS, but in general, and you can ask AMS to implement this. I don't know. High throughput computational workflows are possible that were not imaginable before development of this high quality machine learned interatomic potentials, and it give the path to the workflows that were not available before. Because if everything is done right, the computational performance is tremendous. And with this, I would say, think our group, many members of our group was working on different parts of this project, as well as collaborations in Los Alamos, with University of Florida, and industrial and national funding really appreciated, especially BSF that we're working with on this NAC reactive model. NVIDIA, which also have a lot of support, and different agencies, TACC, SS, Pittsburgh Supercomputing Center. They give our air to breathe. They give our computational resources that we need to do all this work. And with this, thank you for your attention, and probably open for questions. Thank you.
Thank you. Yeah, my name is Matti Hallström. I work as the product manager at SEM, and I will just do a quick demonstration. And here I have the AMS input GUI, and if you select a machine learning potential, you can select different machine learning models. And in AMS 2024, which I'm running here, you can also select these AIMNet2 models. So you can select the model, you can draw a little molecule, and then, for example, if you click the pre-optimize button, and now this is just running on my laptop. I don't have a GPU, so it takes a little while. But now I've optimized this molecule with AIMNet. And you can also calculate, for example, frequencies. So if I save this as a frequency job and I run it, you will also get the IR spectrum actually. And I'll show you that soon. And another little feature. So actually, let's look at the spectrum here. So this is now the IR spectrum of this molecule. And you can visualize the normal modes and get the IR intensities as well. And here at the bottom, highest frequency is the OH stretch. Another little interesting feature, because AIMNet is a committee model, it can predict energy and force uncertainties. So if I displace this little oxygen there, and I instead run a single point calculation, and I remember to calculate the forces, I can save this as a single point and run it. And then when that has finished, I can open it in AMS view. And in AMS view, I can then color these atoms, and I can, for example, color them by the charges, because AIMNet predicts atomic charges like this. So here we see hydrogen is positive, oxygen is negative, which is red. Or I can also color them by the gradients, magnitude, uncertainty. So in this case, we see, for example, that these hydrogens here are red, which means that the uncertainty is very low. But here, when I displace this to a far off equilibrium position, this oxygen, now the forces here on these two atoms is quite high, and the uncertainty is also quite high. So in this way, you can get a feeling for whether AIMNet is certain or uncertain about your chemical system.